Good day, students. In this clip, we're going to be going over part 4 on modeling and optimization. In this part, we're going to be looking at minimizing the distance from a point to a curve. So let's go over the steps again, just as a quick refresher. First of all, we're going to model the situation. To generate a model, you need an optimization function, a constraint function, as long as a well-labeled diagram. Part 2, you're going to substitute. You isolate the variable from the constraint and substitute it into the function that's to be optimized. You also state the domain on the constraints of the independent variable you have as your resultant equation. In part 3, you're going to find the potential extremas, which include the critical points and the endpoints if the interval is closed. If it's an open interval, you do not need to consider the endpoints when finding the potential extremas. And then you're going to classify the extremas in step 4. And in step 5, you're going to state the meaning of your result. Okay? Alright, let's go ahead and take a look at the example. Number 4, it says, what points on the graph of the function y equals 3 minus x squared is closest to the point 0, 2. Also states the minimum distance. Alright, so let's start with part 1, where we're to create a model. Alright, so to accomplish this, what I'm going to do is I'm going to try and sketch the graph of the situation, sketch the curve, and the point. So we have our y-axis, that's my x-axis. So we have this curve right here. What transformation does this curve apply to the standard y equals x squared function? You have positive 3 and minus x squared. So if you have a standard parabola facing up, plus 3 basically means you're going to shift 3 units up, and then this minus in front of the x squared means you're going to reflect the parabola downwards. Okay? So we have a standard parabola centered at the origin. We're going to shift 3 units up, 1, 2, 3. That will be our vertex. And instead of opening up, our parabola will open downwards. Okay? So let's graph the points. Have a set of points here. And then 1, 2, 3. Then go over here. Our parabola will open downwards. Alright, and then the next point goes here, so 1, 2. Alright, this is just a sketch of the situation, okay? So let's go ahead and graph the parabola facing downwards. It's going to look something like this. And then we have the other piece through those 2 points. Let's do that again. Alright, so with these 2 parabolas, with this parabola, we have a point that we are calculating the distance, we're minimizing the distance from this curve to that point. So the point is 0, 2, so we're 0, 2, we have 0, 2 right here, that's the point 0, 2. Okay? So what we're doing is we're going to pick any arbitrary point. Let's see, let's call the point xy. So if you pick a point here, call that point xy. And what we're doing is we're minimizing the distance from that point to the point 0, 2. So we're trying to minimize that distance. Okay? So what we're going to do is we're going to call that distance d. So the length of this segment right here is going to be d. Alright, so what is the distance formula? The distance formula, using analytic geometry, remember, d equals the square root of x2 minus x1 quantity square plus y2 minus y1 quantity square. Okay, the entire thing rooted. So this is your distance formula that we're going to be using here. Alright, so let's take a look at the optimization function first. Optimization. Optimization, we are optimizing a length or distance. Okay, let's call it distance. Since we're going to be using distance formula, that's what we are optimizing. We're looking for the minimum distance. Alright, so in order to use the distance formula, we need 2 points. Okay, so we're going to minimize distance Distance from where to where? Distance from the point 0, 2 and or to the any point xy on the curve. Okay, so all right, so now what we're going to do is determine what x1 and y1 are and x2 and y2. Okay, so the first point is x1, first point, yeah, x1, y1. The second point, x2, y2. So if we substitute these values into our distance formula, that will give us the optimization function. All right, so d equals the square root. Let me use a ruler here since it's going to be a long expression. X2 minus x1. X2 is x minus x1 is 0 square, following this formula, plus y2 is y minus y1 is 2 quantity square. Okay, so that is the expression that we are optimizing. We're minimizing this distance right here. We also need another function or set of functions known as the constraint function. All right, so to find the constraints, we're optimizing subject to a constraint. What is our constraint here? We're constrained by a curve. Okay, the curve that we're constrained by is the curve y equals 3 minus x squared. So we have a constraint and optimization functions. Now let's shift to part 2 of the problem solving process, where we're going to make a substitution. So substitute. If you notice, our distance function is in terms of two variables, which is hard to differentiate in one dimension. So we need to make a substitution here. So what kind of substitution can we make so that this distance function can be expressed in terms of one variable? You see this constraint, that's the beauty of the constraint function. Y equals 3 minus x squared. So let's substitute that into our distance formula. So we have distance equals the square root of x minus 0 is x squared plus, I'm going to change colors here. Instead of y, I'm going to put 3 minus x squared. That is from my constraint function, minus 2 quantity squared. Okay, let's simplify this before we talk about the domain. All right, so to simplify this, this is going to be equal to the square root of x squared plus, and then if you minus 3 minus 2 is 1, so 1 minus x squared squared, and then when you expand that, you follow it out, you're going to have x squared plus 1 minus 2x squared plus x to the 4th. Okay, so the distance formula we're going to be working with, the distance function that we're going to be working with here, that we simplify everything, we're going to have x to the 4th minus x squared plus 1. So what are the constraints on our domain? Let's look at our domain. If you look at this function, what is the domain of x? What are the acceptable inputs for x? The answer is all real numbers. There are no constraints on x. Okay, every input for an x value will have a defined output. So our domain, we have no restrictions on our domain. So the domain for this problem, domain is from negative infinity to infinity. Okay, so that's that. All right, let's look for our potential extremas in part 3. All right, part 3, potential extremas. Potential extrema. All right, so we know that our potential extremas are the critical points and endpoints. In this problem, our domain is an open interval, so our endpoints are not included here, okay, since we do not have any endpoints. So our potential extremas in this problem are basically our critical points, okay? So how do we find the critical points? We find critical points. Critical points are when the derivative, we're dealing with d, that's our function this time, so where d prime is equal to 0 or d prime does not exist. Okay, so these are the two values of x that we are going to be solving for. So let's start by writing down what our distance function is. Our distance function d is the square root of x to the fourth minus x squared plus 1. So let's differentiate this. Remember the differentiation shortcut for radicals. d dx of the square root of x is equal to 1 over 2 root x. Okay? So we're going to apply that here. We also have to apply the chain rule here since we have an input function. Okay, so let's differentiate. d prime equals 1 over 2, differentiating the parent function and holding the inner fourth power polynomial fixed, times the derivative of the input function, which is x to the fourth minus x squared. If we differentiate that, we will have 4x to the third minus 2x. Okay, so our derivative is 4x to the third minus 2x divided by the square root of actually we have a 2 on the outside, so 2 times the square root of x to the fourth minus x squared plus 1. Alright, so to find our critical points, let's start with when d prime is equal to 0. When d prime is equal to 0, we can just focus on the numerator. Set the numerator to 0, okay, because when you cross multiply, the denominator drops off. Alright, so now let's solve this. We're going to factor, we can factor out the GCF here, which is 2x, so factor out 2x. And then we have 2x squared minus 1 equals 0. Alright, so we're going to set the two factors equal to 0. So we have 2x, set 2x equal to 0, and 2x squared minus 1 equal to 0. Alright, so we'll solve this, we'll end up with x equals 0. And then if you solve this, you end up with x equals plus or minus root 2 over 2. Alright, so these are the points where the first derivative is equal to 0. How about when d prime does not exist? To find this out, what we're going to do is basically set the denominator equal to 0 and solve for that. So 2 times the square root of x to the fourth minus x squared plus 1 equals 0. If you divide both sides by 2 and square it, you're going to end up with x to the fourth minus x squared plus 1 equals 0. This is a fourth degree polynomial. We can easily convert this into a second degree polynomial by making a nice substitution. How about we say let u equals x to the second power. If we make that substitution, we're going to have the quadratic u squared minus u plus 1 equals 0. We can solve this using the quadratic formula, where a is 1, b is negative 1, and c is 1. So if we do that, we're going to have u equals plus or minus, we're going to do negative b, which is positive 1. So positive 1 plus or minus the square root of b squared, which is 1 minus 4ac. 4 times 1 is just 4, divided by 2a. Okay? So that gives us 1 plus or minus the square root of negative 3 over 2. Now if you examine this term right here, the radical component, you notice is negative. So our solutions here are going to be non-real. Okay? They're not real solutions, not points we can graph on the graph. Points we can graph on the graph. Alright, so you know what that means? There are no real values of x that satisfy the non-existence of the derivative. So when is the derivative 0? The answer, when is the derivative non-existent? The answer is never. Okay? So this has no solution. So now we know what our potential extremas are. Potential extremas. Potential extremas in order are negative root 2 over 2, 0, and root 2 over 2. Okay, now next what we're going to do is we're going to classify them. There are two ways we can do this. Part 4, which is classify. We can use the first derivative by looking at when the function is increasing and decreasing around the critical points. And if it's increasing and then decreasing, then we know we have a max. If it's decreasing then increasing, we have a min. Okay? Or we can use a quicker method, which is the second derivative. All right? So if it's concave up, we know we have a min. If it's concave down, we have a max. So I like to use the second derivative because it's faster. All right, so we know that all right, so the derivative d prime is equal to 4x to the third minus 2x, that divided by 2 times the square root of, and again, the square root of the fourth degree polynomial, square root of x to the fourth minus x squared plus 1. Okay, now let's look at this. I was thinking about using the second derivative test here, but to differentiate this using the quotient rule with all the radical is going to be a mess. So I think let's use the first derivative test. I think that will be much easier to handle. Okay, so what we're going to do here is let's make up our number line and then create intervals that we're going to test. Okay, so that will give us the definitive answers that we're looking for. So our critical points are negative root 2 over 2 is approximately negative 0.7. You can check that with your calculator. And then we have 0. And then we have positive root 2. These are the potential extremas that we have, okay? And then this is approximately 0.7. Okay, so we wanna look for the minimums, okay? We could have one or more, so that's what we're looking for. Now, for interval 1, we're going to let's test x equals negative 1. For interval 2, let's test x equals negative 1/2. For interval 3, let's test x equals 1/2. And then for interval 4, let's test x equals 1. Okay? All right, so we're going to evaluate the first derivative at these points, and then see where it's increasing, decreasing, and then know where our max and mins are. Okay? So let's start with interval 1, x equals negative 1. Now, if you look at this function, the derivative, all we care about is the sign. Okay? The denominator has a square root. Can a square root expression ever yield a negative output? The answer is absolutely not. So since the denominator can never be negative, we just focus our attention on the numerator. Okay? So let's evaluate the numerator. It's going to be 4 times negative 1. The sign of the numerator tells us the sign of the entire expression. Okay, 4 times 2 times negative 1. If you evaluate that, you have negative 4 plus 2, which is negative. So it's negative on interval 1. The first derivative is negative, which tells us something about the function, that it's decreasing, right? Interval 2, we're going to test x equals negative 1/2. 4 times negative 1/2, just looking at the numerator, because that's what tells us the sign, times 2 times negative 1/2. That's going to give us negative 4 over 2, which is negative 2. And then if you multiply this together, it's going to be slight mistake here. Let me make a real quick correction. This is supposed to be to the third power. The 1/2 is to the third power. So if we raise negative 1/2 to the third power, we're going to have negative 1/8. Multiply that by 4. We're going to have negative 4 over 8. Negative 4 over 8 and then if you multiply these two minuses, you have plus 1. Okay, so negative 4 by 8 is negative 1/2, plus 1 is positive 1/2, so it's going to be positive. Positive on interval 2, the first derivative. Alright, so what's the sign of the first derivative on the third interval, where x is equal to positive 1/2? Well, let's evaluate the numerator again, because that is what tells us the sign of the derivative. Okay, so 4 times 1/2 to the third power minus 2 times 1/2. Okay, so in this case, we're going to have 4 over 8. It's positive this time. 4 over 8. And then times minus 1. Okay, so this is 1/2 minus 1. Our answer is going to be negative. Alright, so it's negative on the third interval. Now let's examine the last interval, interval 4, where x is equal to 1. Okay, so we have 4 times 1 to the third minus 2 times 1. So we basically have 4 minus 2, which is positive. Alright, so it's positive on interval 4. So it's positive right here. Okay, so what is happening in what interval? We can clearly see that the function is decreasing on interval 1 and decreasing on interval 3. Okay, and the function is increasing on interval 2 and increasing on interval 4. So what does that tell us about the extrema? We have, since it's decreasing and increasing here, this is a min. Since it's increasing and decreasing here, this is a max, relative max. And since it's decreasing and increasing here, this is another relative min. Okay, so we have 2 relative minimas in this function. Okay, so those are the values that are where our minimum distance are. Okay, so which one will give us a smaller distance out of the 2? Well, we actually have to compute what the distance is for those 2 values. Alright, so before we determine which of the distances are small, is the smallest, or even if they're equally small, let's write down what we can decipher from this chart right here. We have a relative max at x equals 0, and we have 2 relative mins, relative min at x equals negative root 2 over 2 and root 2 over 2. So the question is, which yields a smaller distance, or maybe they're both equally small. So to determine what the minimum distance is, we're going to evaluate the function d. We know what the d function is equal to the square root of x to the 4th minus x squared plus 1. Now, if you take a look at it, what happens when you input these 2 into this function? You're going to get exactly the same output because these 2 variables are raised to the even power, so the negativity is of no consequence. Okay, so what I'm saying in essence is d of, let's change that to parentheses, so d of negative root 2 over 2 is going to be exactly the same thing as d of root 2 over 2. Because where we are plugging them into, they're going to be raised to the second power, to an even power, which nullifies the negativity. Alright, so let's plug it in, since we're going to get the same thing. It's going to be the square root of 2 over 2 raised to the 4th power minus the square root of 2 over 2 raised to the 2nd power plus 1. Okay? Now, if you do the calculations, you're going to have the first term, root 2 to the 4th power is 2 times 2, which is 4. 2 to the 4th power, 16, minus root 2 squared is 2 over 4, plus, we can express this as 4 over 4. Okay, 1 is the same thing as 4 over 4. 4 minus, and then we have to, let's simplify this a little bit more. We're going to have, okay, we can divide the 4 over 16 we can reduce that to 1/4. So we have 1/4, and then evaluate these two, we have plus 2/4, which equals the square root of 3/4, which is root 3/2. Okay, so that's the minimum distance. All right, so what are the points? We know the x-coordinate of our points, but we also need the y-coordinates of our points, right? So when remember the question asked for the points that are the minimum distance to 0, 2. We know what the distance is, but we actually have to figure out what the points are. So when, let's put this for a minute. So when x is equal to the first value, when x is negative root 2/2, what is y? Well, we know the constraint function tells us what y is, right? So y is equal to the 3 minus x squared, all right? And then, so if we plug in this value, we're going to have 3 minus negative square root of 2/2 squared. Okay, so that's going to become 3 minus, if you square root of 2, you have 2/4. Okay, and then we can express this as 12/4. 12/4 minus 2 is 10/4, which reduces to 5/2. Okay, and then when x is equal to the square root of 2/2, we're going to have the same answer, right? Because we're squaring the term, so it's going to be 3 minus the square root of 2/2 squared, which is going to be 3 minus 2/4, which is also 5/2. Okay? All right, so now we're ready to write our conclusion. All right, so conclusion, which is part 5. The minimum distance from the point from 0, 2 on the graph y is equal to 3 minus x squared is, what did we find the minimum distance as being asked? This was the minimum distance when we inputted the x value into the distance function, right? So the minimum distance is root 3/2. Minimum distance is root 3/2, and you also asked for the points, and the points are x, the first one was negative root 2/2, and the y value was the alpha we got, which is 5/2, and the second point was root 2/2, and the y value was 5/2. Okay, so that's that. Good day, students. In this clip, we're going to be going over 2 examples on related rates. We're going to be looking at cubes and squares. Before we get started, let's do a real quick review on dimensions. So if we have length raised to the first power, that's basically a length. If we have a length raised to the second power, this is an example of area. That is area. And then when we have a length raised to the third power, length times width times height, that represents volume. So if we examine the units of the values given, we can easily determine what they are representing. Are they representing a length, area, or volume? Okay. So now let's take a look at question number 1. It says, so number 1 reads, it says, an ice cube of perfect size melts uniformly at a rate of 27 centimeter cube per second. If the cube retains its perfect form while melting, at what rate are the sides shrinking when each side is 3 centimeters long. So let's take a look at the different values here that are provided and then see what we are looking for. First of all, if we look at this value right here, 27 centimeter cube per second, this 27 centimeter cube represents a volume and second represents time. Okay, so we know that dV dt, instantaneous change in volume, is equal to 27 centimeter cube per second. Now, since the cube is melting, the direction is going to be negative. Next, let's take a look at what other information we have. It says, at what rate are the sides shrinking? So let's say we want to call the side of a cube S. So it says at what rate? The rate of the shrinkage of the sides is known as the S dt. And we do not know what that is. Alright? And then it says when each side is 3 centimeters long. So we're also informed that the side length S is equal to 3 centimeters. Okay? So what we need is an equation with dV dt, ds dt, and S, so that we can plug in these two values, dV dt and S, and solve for ds dt. Alright, so we're looking at a cube. Let's make a sketch of a cube. Alright, so there goes the sketch of my cube. So let's call each side S. So we have S here, and S here, and S here. So what is the formula for the volume of a cube? We know from geometry that the volume of a cube is length times width times height, and they're all S's, so it's basically S to the third power. Okay, so let's find the related rates equation, the equation that relates dV dt with ds dt. So we're going to differentiate implicitly. The left side will differentiate with respect to time, derivative of v as 1 times dV dt. On the right side, using the power rule to differentiate s to the third power, we'll have 3s to the second power. And using chain rule, differentiating implicitly, we have the s dt. Okay? So let's rewrite this equation. We have dV dt equals 3s squared ds dt. Okay, so now if you look at what we have listed here, it works perfectly. Remember, we needed dV dt, an equation with only dV dt, ds dt, and s. So we have dV dt, ds dt, and s with a constant. So we can plug in dV dt and s into this equation and solve for the unknown, which is the s dt. Okay, so let's isolate the s dt. To do that, I like to isolate the s dt before solving. So to do that, we can just multiply both sides by 1 over 3s squared on the left side, and on the right side you multiply by 1 over 3s squared. On the right side, notice that is 3s squares cancel out, and we have the s dt equals 1 over 3s squared dV dt. Now let's input the values we know. We know s is equal to 3 centimeters, and dV dt is negative 27 centimeters. So let's plug that in. We have the s dt is equal to 1 over 3 times 3 squared times dv dt, which is negative 27. And if you work this out, you have 1 over 27 times negative 27, which equals negative 1. Now, since this is a length, one dimension is going to be centimeters, and the unit here is seconds. The unit of time is seconds. All right, so let's write down what the answer means as a sentence. The side length of the cube is changing at -1 centimeter per second when each side is 3 centimeters long. Okay, so that's that. Okay, let's take a look at number 2. It reads, a square grows at a rate where its diagonal increases at 6 centimeters per minute. Find how fast the area of the square is increasing at the instant that its diagonal is 8 centimeters long. So let's go over this list of units on the side. The unit of length in this problem is centimeters, and the unit of time is minutes. Okay, so let's see what we can get from the problem. It says the diagonal is increasing at 6 centimeters per second. So it's talking about the diagonal. So let's call the diagonal L. So let's L equals length of the diagonal. And let us also define A as the area. Okay, so A equals area of the square. All right, so let's look at this problem. It says the diagonal increases at 6 centimeters per minute. So what does that mean? It tells us that the LDT, the instantaneous change of the diagonal per unit time, is equal to 6 centimeters per minute. And it says how fast is the area of the square increasing? So we're looking at a change in area. That's the A dt. That's what we're looking for. So it is unknown. And it says we need to find the A dt the instant that the diagonal is 8 centimeters long. So when L equals 8 centimeters. So we need an equation with just the LDT, the ADT, and L, so that we can input the values of the LDT, L, and solve for the ADT. Okay, let's go ahead and see if we can come up with an equation that relates L, the length of the diagonal, and the area. So let's sketch a square. There goes our square. So let's indicate where the diagonal is. That's the diagonal. Now let's say the square has side lengths S and S, and this right here represents the diagonal L. Now what is the area of a square? The area of a square is S squared, length times width. This formula relates the area and the side length, but we need a formula that relates the area and the length of the diagonal. So is there a connection between the side lengths and the length of the diagonal? Absolutely. They have a Pythagorean relationship, so we know that L is equal to the square root of S squared plus S squared. So we call this ABC, and we use A squared plus B squared equals C squared. if we substitute and isolate L, we'll have this equation right here. So L is basically the square root of 2s squared, which equals s root 2. If I isolate s in this equation, I can clearly see that s is equal to the length of the diagonal divided by root 2. So if I call this equation 1, and I call this 2, I can substitute L over root 2 for s in the first equation. Remember, we need a formula that has just the area and the length of the diagonal. So upon differentiation, we can make a substitution and solve for the ADT. Okay, so let's make the substitution. We are going to have the area, A, equals L over root 2 squared. All right, when we square the top and the bottom, this becomes L squared over 2. Okay, so now we have A is equal to L squared over 2. We are going to differentiate implicitly. So we differentiate the left side, we'll have the A dt on the right side equals 2, using the power rule, L over 2 dl dt. Let's simplify this a little bit more. We're going to have, just make it look pretty, the A dt equals, the 2's cancel out, L dl dt. Okay, so now we're ready to look for, what are we looking for? Let's go back to the question. We're looking for the ADT, given the fact that the LDT is 6 and L is 8. So let's plug in those values into this equation. The ADT is simply going to be 8 times 6, which is equal to 48. What is the unit of area and time? The unit for area is length squared. The unit for length in this problem is centimeters. And the unit for time in this problem is minutes. Okay, so let's write a conclusion. The area of the square is grown. Good day, students. In this clip, we're going to be going over an example on optimization and modeling. This situation involves a cylinder being inscribed in a cone and determining the maximum volume. Okay, this is part 2 of a 3-part series, so you can go to my playlist to access the other parts. Okay, so when solving optimization problems, these are the 5 steps I normally require of my students. First of all, you generate a model using a well-labeled diagram. The models are going to be 2. You're going to have your optimization, a primary function, and a constraint function. Okay. Part 2 involves a substitution process where you're going to express your optimization function in terms of one variable by substituting and explicitly solve for variable in your constraint function into the optimization function. That makes it easy for you to differentiate. Okay. And then you also state the domain, the reasonable domains for your new function in terms of just one variable. In part 3, you're going to find the potential extremas. Those include the endpoints and the critical points. Endpoints are applicable to just both interval situations. And in part 4, you're going to classify your extrema using the using the second derivative test is basically the fastest way to do that. And then lastly, you just state the meaning of your result. Okay. All right. So let's take a look at the example. This is number 3. It says a right circular cylinder is inscribed in a cone with height 12 and base radius of 4. Find the dimensions of the cylinder that maximizes its volume, the volume of the cylinder, and what is the maximum volume of such a cylinder. Okay, so this is a graphic I have right here of a cylinder inscribed in a cone. Let's start by creating a model. I need 2 equations. I need my optimization function, and then I also need my constraint function. All right, so let's start out with the optimization function. Optimization, the function to be optimized, optimization function. Um, all right, so we're optimizing the volume of a cylinder. So what is the volume of a cylinder? We know it's the area of the base times the height. So what I'm going to do is I'm going to create a two-dimensional replication of this situation right here. So let's say we have in 2 dimensions, this is the cylinder right here. Okay, so let's do it this way. All right, so that's the cross-section representation of this situation right here, sliced down the middle. So this is the cone, and this is the cylinder right here. So let's do it this way. Let's say that we want to call the height of the cylinder. This is the height. Let's say the height is y, and we're going to call the radius of the cylinder x. Okay? We do not know what they are yet, right? So we're going to use variables to represent them. Okay, so the height of the cylinder is y, and the base radius, let's call that x. Okay, all right, so now that we know the height and we've declared the height, the variables for the height and the radius of the cylinder, now we can find the volume, okay, which is what we are optimizing. So we know that. Let me just write down the formula for volume before I use it. So volume is equal to pi r square h, area of the base times the height. So in this case, v is going to be pi, the radius is x, so it's pi x square y. Okay, so that's the optimization function for you. Now, the constraints. What are the constraints on the dimensions of the cylinder? So constraint or the secondary function. So for the constraint, we're constrained by the dimensions of the cone. Okay, so we have this triangle right here. This rectangle, the cross-sectional dimensions of the cone must reside inside, of the rectangle must reside inside that of the cone. All right, there are two ways that we can find the equation for the constraints. One method is by using similar triangles, and the second method is by using the equation of a line. All right, I'm going to show you both methods, and then you can basically pick the one that you like the best. Okay, I prefer similar triangles because it's straightforward and I don't need to, do any hard work with that. So let's see. If I want to use two similar triangles, I need to basically make a statement that corresponding sides of our similar triangles are in proportion. So we have the entire length of the cone. We know the cone has a height of 12 units, and the radius of the cone is 4 units long. Okay, so there goes the radius of the cone. So now I'm going to use the similarity postulate here to state that the angles are similar. Well, how do we know that our two triangles are similar? Well, first of all, what two triangles am I talking about? Let me highlight them for you real quick so you can see. This is a smaller triangle right here, the red triangle. Okay, this is a smaller triangle right here. And then the bigger triangle, the entire thing is the bigger triangle. Okay, let me put that in, let's put that in green so you can see the two similar triangles that I speak of. Okay, green. Okay, so see this triangle right here? This big one. This one is the other triangle. Okay, that one right there. So the green triangle is similar to the red triangle. Okay, so how do we know that they're similar? Well, since this side, this vertical line right here is parallel to this vertical line right here, these two angles form corresponding angles. So these two angles are congruent. Okay, and then these two angles are the same. They share a common angle here. So by the angle-angle similarity postulate, we can conclude that these two triangles are in fact similar. So this side corresponds to the entire length, and this side corresponds to this side right here. Okay, All right, so we need to find the dimensions of our smaller triangle. Okay, so we know that the height is y of our smaller triangle, but we need to find out the base, this distance right here. So since the entire thing is let's change the color of that. Since the entire thing is 4 units long, and we know that this portion is x units, so what's going to be left here is the question. So if the entire thing is 4 units and this portion is x, what's going to be left is the difference, right? It's going to be 4 minus x. Okay, so we have this big triangle right here that is 12 by 4, and we have a small triangle right here that is y long by 4 minus x. Okay, all right, so let's state it right here. Method 1, for finding the constraints, method 1 is using similar triangles, all right, similar triangles. All right, so just to make sure everybody understands this, I'm not trying to bore you here. I'm just going to draw the two triangles separately so you can see what I am doing. So we're going to draw first the bigger triangle, and then we'll draw the smaller triangle that it's similar to. Okay? All right, so I'm now going to populate the measures, and then we can use the similarity postulate to basically make statements about the proportionality of corresponding sides. This entire side is 4 units long. This side is 4 minus x. This length right here is 12 for the big one, and then for the small one, this is y. All right, so corresponding sides are basically in proportion. So what statement can we make here? We can say that y, the height of the smaller one, the y over 12 is equal to 4 minus x, the base, the shorter leg of the small one, divided by the shorter leg of the big one over 4. Okay? So this is basically elementary geometry we're using over here. All right, so that statement, I like to isolate a variable so I can make a substitution here. So we have two variables. So what I can do here is I can get y isolated by multiplying both sides by 12. Okay, so I multiply this by 12, and then I multiply this side by 12 also. So what's that going to yield? It's going to give me y equals 4 goes here 1, 4 goes here 3 times. Distribute the 3, 12 minus 3x. Okay, that's a nice constraint. So that was one way of doing it, using similarity. Another way of doing it is by using the equation of a line. So method 2, we're going to use y equals mx plus b. Okay, now to do that, just imagine that this right here, this is your y-axis, okay? And then imagine that this right here is your x-axis. All right, so, and then this side right here is the equation of a line, and this is a point on the line, okay? So, what is the equation of this line right here? If you look at this line, this is a y-intercept. If you're going from 0, 0, all the way, let me make my y-axis a little bit longer so it's obvious what I'm doing. Let's put the line here 1 second. So that's 0, 0, coordinate system. Should in both directions. Okay, so if that is 0, 0, and you go 12 units up, so what's the y-intercept of this line going to be? This entire line right here, if you go 12 units up, it tells you that y-intercept is b, which is 12. So for that case, we know that b is going to be 12. That's your y-intercept. Okay, now what is the slope of this line? Starting from 12, you drop down 12, that's your negative rise, and you run 4. Okay, so m is rise over run, which is negative 12 because you're dropping, and your run is 4. And if you reduce that, you have negative 3. All right, so if you plug in b and negative 3 into the y equals mx plus b equation, you have y equals negative 3x plus 12, which is the same thing as what we had before. What did we have before? 12 minus 3x is the same thing as negative 3x plus 12, because we know about that addition commutes, okay? So that's basically our constraint function. All right, so whichever method you like, you can use. I like this one better, so that's the one I use. So let me box my constraint function. This is my constraint function right here. Variation 1 or variation 2, they're the same. And then my optimization function is this one right here. All right, let's move on to part 2, where we're going to be doing this substitution. All right, so part 2, we're going to substitute. The nice thing here is that we have already isolated a variable in our constraint function, so we don't have to do much work. We know that v in terms of two variables was pi xy square x square y, and then when we make a substitution, we know that this is this, and y is equal to 12 minus 3x. So if we make the substitution of this value of y in here, our volume function that we're going to optimize it in terms of just x is going to be pi x squared times 12 minus 3x. Okay? And then to make it easy to differentiate so we don't have to use the product rule, we can just distribute pi x squared to these two terms right here. So v of x is going to be 12 pi x squared minus 3 pi x to the third. Now what's the domain? What is the domain here? What are the constraints on x? How small can x get? Well, let's look at the triangle. If this cylinder were to have 0 radius, it would just be a long straight line, right? So if that is zero radius, you have just a straight line. It's going to be a line. That's as small as x can get. How big can x get? X can get as wide as this. Okay? In that case, you have a flat line as your cylinder. Okay? So when x is 0, you're going to have a situation like this. You have a cylinder that looks like this. I don't know why you want to have a cylinder like that, but that's the situation when x is 0. And then when x is the maximum value of 4, you're just going to have a line that's 8 units long and has 0 height. Okay, and that will also yield a volume of 0 also. So these are your two extremes. X can be 0 or x can be equal to 4. Okay, remember x is your radius, it's not your diameter. Okay, so that's x right here. Okay, so our domain is x goes from 0 to 4. There are no restrictions on this because it's a cubic function, no domain constraints, so these endpoints are good. All right, so let's move on to part 3. We're going to look for potential extremas, extremas. All right, so the endpoints are automatically potential extremas that will be considered and should be considered, but we also have to find the critical points, okay? Because we know potential extremas are your endpoints and critical points, okay? All right, so we already know our endpoints, so let's look for our critical points. So critical points, what are critical points? Critical points are where are critical points? Where the v prime in this case, because this is a function, v prime is equal to 0 or v prime does not exist. That's what our critical points are. All right. So let's focus on the first one. Where is v prime equal to 0? So let's recall the volume function. V of x is equal to 12 pi x squared minus 3 pi x to the third. Let's find the first derivative of that. V prime of x is equal to 24 pi x minus 9 pi x squared. All right, so set that equal to 0. You have 24 pi x minus 9 pi x squared equals 0. So let's factor out, I'm going to be lazy here, I'll just factor out x, even though that's not the GCF. So factor out x, and then you're going to be left with 24 pi minus 9x equals 0. Now we're going to use the zero product property, set x equal to 0, or the other one, 24 pi minus 9x equals 0. This is already solved. this one is going to be x equals 24 over 9, right? Oh snap, here's a pi here. Sorry about that, let me put that back in. Kind of drop the pi off in the process. So put the pi back here, pi x. Okay, equals 0. So when you solve for pi, you subtract, you have negative 24 pi over negative 9 pi. Okay, which reduces to, divide both sides by 3, 8 over 3. Okay, so that's your x value. You notice that one of our solutions intersects with the lower bound of our domain, right? Okay, so now, when does v prime equal, when is v prime non-existent? This is a cubic function. We don't have any corner, cusps, vertical tangents, or discontinuities. It's smooth and continuous, so it's always differentiable. So when is v prime d/e? Never. Okay. All right. So our potential extremas that we're going to consider, potential extremas are the endpoints. Let's put them in increase. So 0, and then let's put it in order. 8/3 and 4. Okay? This is an endpoint and a critical point. This is a critical point, and this is an endpoint. So these are the three things we're going to evaluate to find the maximum. Okay? All right, now let's take a look at part 4. That involves classification of the extremas. It turns out that for this problem, we don't even have to use the tool of calculus to determine which is a max or a min. We can just evaluate these points, put this point into the function, and then we can tell if they're maxes or minimums. Okay, so let's see. Let's call it classification or classify. All right, so since these are our endpoints and critical points, if we plug all of them into the function, the biggest one would tell us that's basically the maximum. And then if we have smaller ones, they could be relative mean or absolute mean, whatever. But let's just plug them in and see what we have here. Okay. So we talked about the endpoints earlier as creating zero volume. So if we do v of 0, for example, plugging 0 into the original function, 12 pi times 0 squared minus 3 pi times 0 to the third. That's going to be 0. And then even though if you compute v of 4, 12 pi times 4 to the second power minus 3 pi times 4 to the third, plug that into your calculator, you'll get 0 also. Okay? Now let's plug in this one, v of 8 over 3. V of 8 over 3, we're going to have 12 pi times 8 over 3 squared minus 3 pi times 8 over 3 to the third. If you plug this in your calculator and work this out, you're going to end up with 256 pi over 9. Okay? So you can clearly see that this is the maximum. Is an absolute, is a relative and absolute max. Relative and absolute max. And then these right here are your minimum. But we don't really care about these. We just care about the biggest volume, so to speak. Okay, so this is the biggest volume. And then we're going to conclude that these are the minimums too, because there's no way you can have a negative volume. Okay? Alright, so this is our absolute max right here, just by plugging in. But you can also verify using calculus. Okay, so let's just do x right here. This is not necessary, but if you wanted to verify using the second derivative test, all you need to do is you have a critical point, and if the second derivative is negative, you have a downward concavity or it's concave down, and that indicates that you have a maximum at that critical point. All right, so we know that v prime of x was equal to 24 pi x minus 9 pi x squared. And then the second derivative, v double prime, is going to be 24 pi minus 18 pi x. Okay, so we want to evaluate the sign of the second derivative at this critical point. I just want to show you that this is in fact a maximum. Okay, so we're hoping to get a negative output, so that will indicate downward concavity, and then that will tell us that it's a maximum. Okay, so v double prime of 8 over 3 is equal to 24 pi minus 18 times 8 over 3, 18 pi times 8 over 3. Okay, that equals 24 pi minus 3 goes here 1, 3 goes here 6, 6 times 8 is 48. So 48 pi. And then when you subtract it, you have negative 24. So negative 24 pi. So v double prime is negative here. Okay, so since 8 over 3 is a critical point, and v double prime of 8 over 3 is negative, there is an absolute maximum at 8 over 3. Okay, because you know what downward facing concavity looks like, right? It looks like this. So if you have a downward facing concavity at an extrema, that is absolutely a maximum. Okay, all right, so that's that for the classification. We found a maximum, but that's the x value. We have to state the dimensions of the maximum area. Okay, maximum volume. So part 5 is our conclusion. Let's take the dimensions first. Dimension of maximum volume of a cylinder with maximum volume. Cylinder with maximum volume. The radius is x, right? So the radius is x, and x is 8 over 3. And then the height, remember what we said the height was earlier? The height is y, and that's given by 12 minus 3x. And then we know x is 8 over 3, right? So it's 12 minus 3 times 8 over 3. 3 goes here 1, 3 goes here 1, 8 minus 12 is 4. So the height is 4, the radius is 8. Okay? And then the maximum volume is what you get when you plug in 8 over 3 into the original function. And I think we've already done that. We did that right here when we're determining which one is the maximum. So v of 8 over 3 is the maximum volume. Okay? So we're going to do simply v of 8 over 3, and then we have 256 over 9 pi. All right? And this is in cubic units. This radius is in units, and your height right here is in units. Okay, so there you have it. Thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here. I really appreciate it. And please post a comment to let me know what you think about this clip, and give me a thumbs up if you liked it. More clips can be found on my website.com/calculus. Thanks again for watching, and have a wonderful day.